to come here and participate in this stimulating workshop. So when I was deciding what I might present here, Sasha and I were working on this compound, and the title of this workshop is Spin-Orbit Coupling in Oxides, and I'm sure with emphasis on transition metal oxides and so forth. I had to decide whether it was legal to talk about uranium ditelluride, but I decided it is because tellurium here is just heavy oxygen, right? It's very heavy oxygen, and uranium down here is just very heavy transition metal. It's a different shell that's open, but uranium ditelluride is just a very heavy transition metal oxide, right? Okay, so I'm going to talk about uranium ditelluride, and unlike many of the contributed talks over the last several days, this is going to be sort of show and tell. No real detailed results, I would say, and not a lot of numbers. Okay, so let's just go ahead and consider the structure of this. The structure is not going to be of great import in what I'm talking about, but it is orthorhombic, body-centered, space group IMMM, so it has inversion. And it is, if you look at nearest neighbor uranium-uranium distances, then you can call this a chain along the A-axis. This is A coming out of the board, B and C in both of these figures. This shows you the crystallographic unit cell. And okay, the site symmetries are fairly low. Okay, the excitement is mostly related to nearly ferromagnetic superconductivity in this compound. And another title paper is likely non-unitary triplet pairing, and some people say likely unitary triplet pairing, and so forth. All right. This was first reported a year ago, the new results. The compound's been around for a while, but it just hadn't been studied at low temperature and high magnetic field and so forth. And I listened to the talk online of Jean-Pierre Paglioni. He gave it at KITP in Santa Barbara a few weeks ago. And this is one of the slides, and this is their 6 publications, 3 published at that time, and 3 more submitted. All right.
Sorry, what's the TC?
What?
What's the TC there?
TC?
Yeah.
1.8. It's not 200 Kelvin, no. Okay, so science publication, Nature Physics, so forth. That's of interest because I'm going to call this University of Maryland NIST collaboration because that's Jean-Pierre Paglioni, and Nick Butch is the other senior author from NIST. Okay, publications from Dai Aoki and Jacques Fluquet. And most of these are published. And in fact, 2 or 3 of these were published before the group who started finding the exciting results got their papers finally published in Science and Nature Physics. That's the sort of thing that happened. Okay, so there are already these 15 papers published in 1 year. Well, a few still in the archive. All right, so at least in 2 groups, this is a very active field of research. Some data from the first archive posting. That's still good data. At the left-hand side, this is M over H. This is M over H, yeah, versus temperature. And it just shows that for the field along the A-axis, things are much different than the B and C axes. This just shows resistivity versus temperature for 2 different orientations of the field. It's a heavy fermion material. A very poor conductor up here. Well, pretty good metal, but down here the resistivity is a few microohm centimeters. Very good heavy fermion metal. This is just showing M versus H, back and forth, no hysteresis, no magnetic ordering, down to the lowest temperature measured, and in this paper that was 0.4 Kelvin. Okay, and this, I don't remember what that is, but this is, the susceptibility indicates Ising-like behavior with A being the easy axis. No magnetic order, heavy fermion behavior, and the TC transition is seen right down here, just a little below 2 Kelvin. A little bit more data. This is a close-up of the TC transition in this sample. Susceptibility is more abrupt. The heat capacity right here. This is the night shift. There's no change in the night shift here. Actually, more recent data finds a tiny, tiny little change, which some people find interesting at TC. Okay, it's an interesting question whether there's none or there's some, and it's very small. Okay, the heat capacity is interesting. Here is TC, the usual lambda peak. It comes down, but it doesn't go to 0. Here, it's measured down to 0.4 Kelvin, stops right there. The extrapolation goes to that point. The extrapolation from the normal state gives a gamma of 120 millijoules per mole Kelvin squared. That's heavy fermion, clearly heavy fermion. And this extrapolates to half of that value, to within 1%. And this is the University of Maryland NIST data, but the other collaboration got exactly the same results here, measuring to about the same temperature. So something's wrong here, correct? Heat capacity in superconductors goes to 0, and it goes to 0 in different ways. It can have a full gap, like BCS, or it can have point nodes, be fully gapped, point nodes. This shows the angular behavior of transport, thermal conductivity for a point node. In this compound, this is the one, Peter, that I was mentioning yesterday, and the year. Or you can have line nodes. All right, that's it. But heat capacity goes to 0.
So is it not specific heat sample dependent?
No, it's very reproducible. It's very reproducible, different samples and the two groups. Okay.
It's like unitary, non-unitary.
So even worse, right? Okay. So this is from this overview, but from Matsuda, Izawa, and Vector on this sort of thing. All right, so something else can happen. And that is, this is a paper, PRL, a year or two ago, I forget, Agterberg, Bryden, and Tim. And I'm not going to go through any of the argument. It does require broken time reversal symmetry, and they demonstrated in a 4-band model. But what they show is that it's possible in a superconducting state to have an area of 0 gap on the Fermi surface. And if it's an area like this for a spherical Fermi surface, it can reduce, you change parameters, it can reduce to a line node. If it's something like this, it can reduce to a point node. So in some sense, in that sense, they're connected. But this is what got me really interested, exciting, 6-8 months ago, whenever Sasha and I started work on this. Okay, I don't want to make too big a deal of this because, okay, here's the data. This is data down to 0.4 Kelvin. Now, if you go down to 0.04 Kelvin, which is right here, 40 millikelvin, aha, it doesn't extrapolate to a constant there, which is half the normal state gamma, but it turns up. Okay, so what they've done, let's just compare this right here. So if we take those two curves and put them on the same scale, then here it is. Okay, and now what they've done is to fit this data to, and to make things clear, I'll just go to the next slide. They fit it to a curve like this, which is t to the minus 1/3. That's one of the fitting parameters, but it came out to be that way. The phonon heat capacity is known, and the rest, so it's phonon, that's that divergent part, and divergent, so to speak, at t going to 0. And in the superconducting state, they fit it to a t squared. This is c over t, so that would be t cubed for c, and just the normal state gamma above tc. Fit this, they get a good fit.
Is it something connected with something like Schottky nuclear?
No, they ruled that out. I can't tell you, I can't remember why, but they ruled that out. Yes.
So the difference between the total and the electronics, so they, of course, we are at very low temperatures. At some point, they are already subtracting anything that comes from the lattice, from the phonons. But so which is the difference now between the total, so the open symbols and the full symbols? Because we have
Green and blue.
No, it's
Yeah.
No. I'm talking about just the experimental data.
Yeah.
So there's
This-
the C total.
This is the electronic.
Okay. So it's
The red's the electronic.
Full is open, minus green, minus blue.
So the full is when you go this
Just
line
start
up
this.
and because they are so dense.
Yeah.
And
Add
when
these
they do
three
the
together.
subtraction, they consider it's the contribution of these two terms.
Yeah. So there's 1, 2, 3 parameters in here.
Okay.
This is known. Oh, 4 parameters. All right. So they get a good fit. Now there's a bit of a problem with this, which I sort of brought up with Jean-Pierre in email, but not so explicitly. This can't be t to the minus 1/3. Can't be a very serious thing here because you integrate that to get the entropy and look at higher temperature.
What is the physical meaning of
There's no physical meaning of it. As they said they also tried to fit it, or they also tried to fit it to some sort of logarithmic term. They didn't specify what logarithmic term, but this gave a better fit, and it's just a fit. But what they like is that it gives a good fit, and it gives this point node sort of behavior here. And then they seem to have more or less forgotten about this heat capacity down here, this extra entropy. They know from thermal conductivity measurements that it's not itinerant carriers, some sort of localized something. And it's assumed to be the same in the superconducting states and the normal state if the normal state will be reduced that low by...
Do they see universal thermoconductivity?
Hmm?
Do they see universal thermoconductivity as you expect to see for line nodes? Like impurity independent thermoconductivity?
I think thermal conductivity is very consistent with their determination from several different experiments.
If they are normal electrons, then it would not work. Thermal conductivity can distinguish very clearly from presence of normal electrons or the line nodes broadened.
The thermal conductivity goes to 0 like a point node prediction would be. A lot of the data in these 15 papers are consistent with point nodes and the gap. All right, so when you just look at the electronic part, this is the t cubed in C, and then the normal state. All right, so these extra excitations, the entropy, whatever, is fit, and then more or less in the papers that have appeared so far, not been given any extra attention. All right, this is the sort of thing that happens when you apply magnetic fields of 20, 40, 50 Tesla at the high magnetic field lab. And this is a superconducting state. And then you go above a certain field here, and you get into a different phase. This is still superconducting, but it's a different superconducting character. This is fully polarized, labeled here. And over here is another superconducting phase. There's at least there are 3 different superconducting phases in this particular phase diagram. This is just the angle of the field, and this is the magnitude of the field. And doing other things, the groups see lots of very interesting behavior. So to get to beginning to understand the electronic structure, this is what Sasha and I have done. We used full potential LAPW code, which has a lot of things that he's put into it himself. This particular code, so he didn't like me calling it the Schick Veen2K code. Okay, so we have the LDA plus U in there, and we're using it, but we're using it in a way that he has quite a bit of experience with in actinides, what he calls the orbital polarization DFT plus U, and that is to set U equal to J, to take into account double counting properly for the spherical part of contribution to energy. And let me show you in the next slide that this is not a silly thing to try. A very small U. Spin orbit energy scaled 220 millielectron volts. I was happy to see Roberto quote the number from experiment 223 yesterday. We agree. I looked this up. This is an atomic value. And if the tellurium bands are filled, that's tellurium 2 minus, then you have formally uranium 4 plus, F2. That's formally, this is metal, however, and our calculated F charge is 2.8, so there could well be, and maybe it needs to be, F2, F3 sort of physics in here to understand the heavy fermion nature first. Okay, this is an old paper, one of the early papers doing calculations using DFT, LDA, as Igor said, on a heavy fermion material. Uranium platinum 3, it's a heavy fermion superconductor, TC about 1/2 Kelvin, I think. But you can do very good de Haas van Alphen experiments here. And this is a 3-laboratory consortium, Naval Research Lab, Ching Ping and I, Argonne National Lab, Norman, Los Alamos, Albers and Boring, and Krakow at the College of William and Mary, and then Christensen from Denmark. But 3 national labs here on this paper. And basically, here's the complicated Fermi surface that's calculated just in blind LDA. Completely itinerant F electrons. And this paper, 20 years later, is sort of the final nail in the coffin, looking at things more carefully. Alonzo Rich's group doing more de Haas van Alphen, and just plain LDA gives the best Fermi surface. Now, if you go to uranium palladium 3 instead of platinum, same crystal structure, but obviously from the experiment, the 5F orbitals are localized, and only if you stick those occupied states in the core and don't let them be itinerant, then you get roughly the right Fermi surface here. So the treatment of the 5F orbitals in systems like this is very delicate. You don't really know what to do. Okay, this is a non-magnetic band structure from this DFT plus U orbital polarization, Sasha calls it. This is the density of states, and the blue is uranium, and it's uranium F, and the pink is the tellurium SP. You see just about 3 electrons occupied here, and there's a gap. It's a tiny gap, 0.15 electron volts, and that had already been in the preprint earlier in the year. In this group, we get consistent results. They just do LDA. Point is, for the non-magnetic structure, this correction hardly makes any difference. For the magnetism, that's not the case. All right. This is a paper. It's LAPW again, but they used a sort of 40-year-old exchange correlation potential that changes the bands a little bit. And what you get is these little pockets of holes and electrons and so forth. So that shows how delicate the band structure is. Shouldn't really use anything but the best LDA, GGA functionals here. This is Yanese's group reporting results and varying U in conventional LDA plus U treatment. This is the energy gap. You see U equals 0. It's non-zero, about 15 millielectron volts. And then as they apply U around 0.7, the bands overlap, the gap goes to 0. This is F electron concentration in certain pieces of Fermi surface. I didn't learn a lot from that, but this is for U equals 1.0 eV. That's where it just first becomes, start occupying, well, changing F occupation. And then at 1.1 eV, that's right on the steep part of this curve, the Fermi surface area has changed a lot, it's bigger, and then 2, and so forth. So that's the type of Fermi surfaces that come from this, and this is all unpolarized. There's no magnetic order in here, so unpolarized is certainly a good place to start. That work had already been done. We thought about this since it's an Ising ferromagnet and at very low temperature. The system should be locally ferromagnetic, in some sense, long wavelength spin waves and so forth will be there. So what we focused on is looking at the ferromagnetic band structure, which should have some relevance down here. Okay, so this is the density of states, non-magnetic, has the gap. You let it be ferromagnetic, and it really wants to be ferromagnetic, the substantial energy gain, and it just changes the band structure a lot on this scale of 0.1 eV around the Fermi level. Now, so you could say that uranium ditelluride wanted to be a small gap semiconductor. Magnetism spoiled that, made it into metal, and then there's condo physics that happen. If you take this ferromagnetic calculation and project its spin-orbit coupling is included in almost all these figures, projected on the spin up and spin down, it's almost totally spin polarized. Right here, you see the majority has almost everything there. Now, and it's not just a rigid splitting of spin up and spin down, of course. All right, let's look at one more thing. This is what we just looked at, but over here, if you just do, and this is my postdoc, Yunde Kwan did this, forget the spin-orbit coupling, then you have the magenta line here, it's metallic. Then you turn on spin-orbit coupling with the same U as Sasha used, and you get this gap. So this gap is generated by spin-orbit coupling. This gap in the non-magnetic band structure here is generated by spin-orbit coupling, and then you allow it to be ferromagnetic, and then it destroys the gap again. Okay, so destroyed by magnetism, then there's condo physics, which is far beyond band structure, then superconductivity, and then there's this question of the excess entropy at a very, very low temperature, which is all part of the questions to be studied in the future. This is a spin projected density of states of our ferromagnetic band structure. This is projections onto M sub j character. So the 5 halves are in red, right down here. The 7 halves are in blue. The 5 halves are lower. And in fact, the m sub j equal minus 5 halves and minus 3 halves are almost fully occupied. But on the other hand, the minus 1 half and the plus 1 half are both half filled. So that's what I was referring to in the title. That was a little more specific than it needed to be. But this is very interesting degeneracy, sort of an accidental degeneracy, which occurs in our ferromagnetic band structure. That degeneracy suggests there might be some kind of instability, and we were looking at this when we still thought that there was, well, still thought that there was real normal states within the superconducting gap. So if one looks at these two spin orbitals, plus 1 half, they both have a piece that's proportional to y3, 0. That's the z cubed, I guess. This is quantization axis is along the a axis of the crystal, the easy axis. So both of them have that feature. And so if one forms equal combinations with any number here that has amplitude 1, then one gets these two types of contributions here. There's this one with equal amounts of spin up and spin down, but the same orbital y3, 0, and then there's this other one. And what's interesting is that this part is within 1% of being 1/2 of it, and the rest of it is within 1% being the other half. So it was interesting until it seems that this factor of half and gamma and so forth is not really relevant anymore. This is what our Fermi surface looks like. And it has, of course, it's large, has lots of variation of the Fermi velocity down to very low values, the blue, but it also has quite strong one-dimensional, quasi-one-dimensional character to one of these Fermi surfaces, which, if this is relevant, maybe this could be a contributor to why it doesn't want to order. Because if it ordered the way we have done this with ferromagnetic along the a-axis, then you'd have these Fermi surfaces here, which would promote some instability, some fluctuations, and might keep it from ordering. All right. So this summary just is an outline of things that come to me. There's many opportunities for theory here. There's a lot of experiments that's been done in all those 15 papers. There's the underlying non-magnetic band structure, which has been looked at by 3 or 4 groups. Near ferromagnetic Ising-like magnetic behavior and what inhibits magnetic ordering in this system is a question. A Kondo lattice renormalization to heavy Fermi liquid, so that could well be the F2, F3 fluctuations, intermediate valence or mixed valence fluctuations. Is the Fermi surface renormalized in the heavy fermion state or not, like uranium-platinum 3? Gap function of symmetry, that's what there's a little bit about in some of these papers, theoretical contributions. This residual entropy, if it is real, if it's not something that hasn't, well, it seems to be there and reproducible. But the energy scale for that might be of the order of 10 microelectron volts, or it could be 0. Could be some degeneracy that's essentially perfect degeneracy. And then there are the effects of magnetic fields, pressure, strain, and so forth that's going to, and already is leading to unusual phase diagrams. So that's a picture of where things are at in uranium ditelluride after 1 year of a lot of experimental work by these two groups. So I'll be happy to try to answer questions that you have.
Okay, thank you very much.
So by this orbital polarization, what you do is effectively U and J is the same. So there's no pushing down the Howard lower band, something like that. You just polarize the orbital into one specific orbital. So this is what you do by doing this orbital polarization. So
Is that-
overall the structure remains the same, but you just make the occupation into one.
Is that roughly your
Exactly.
idea?
That was an idea to keep DFT, to stay as close as possible to the DFT and to add what is missing in DFT for those itinerant uranium systems, not only this one, but say uranium, germanium 2, uranium, rhodium, germanium, the same approximation works actually pretty well. It means that not to include the spherically symmetric part of the LDA plus U and include only non-spherically symmetric part, to like in this old orbital polarization correction, but not to use this old orbital polarization correction, but to do it with different numerical technology, which is better grounded in a sense. It's a mean field, but still is somewhat grounded. So, well, indeed, you see, the problem is that there is no real way of justifying using these small values of U. And I was looking for some kind of limit where I could at least support it, saying that I want to include what is missing, what would be in the proper density functional theory, means orbital polarization, in a model way which is provided by LDA plus U, using this U equal to JD.
I think U is quite reasonable, J is too large.
How? No, this is typical J for uranium. How?
5?
Yes.
But the U is very small.
Exactly. And it is an artificial effect.
But if you look at recent paper, uranium antimony, how they are, and they use the U is 4. So
Because they use the solver which cannot handle anything else.
when we compare to Sasha, to uranium telluride and uranium telluride that we were doing in the past, so only uranium and telluride or uranium and selenide, and there the U was also large, it was 2 to 3 eV. So is there a short uranium bond that
No,
gives that-
actually it is well above the Hill limit. The thing is that if you want to use the realistic values of U, you should go beyond the static pitch, because then you are immediately spoiling the specific heat value in comparison with experiment.
That would be difficult to explain, yes.
So, Rosie.
So I have a question. When you show the phase diagram that is plotted, was temperature as a function of pressure? Was that where we have the superconducting phase, then we have a ferromagnetic phase? Which was the?
No, this is magnetic field.
No, it was just
It was just
it
magnetic
was just
field.
magnetic field and angle of the
Okay.
magnetic
It
field
was like at low temperature.
at low temperature,
So
below TC, obviously.
this okay. So but have people done pressure experiments on these? Because JP, he does always pressure experiments. That's why I'm asking. Does one know about the phase diagram under pressure? If it has been around for a long time.
He probably has already done some pressure work, but I haven't read all those papers carefully.
So this was just to clarify, because I didn't put I was not sure what was the phase diagram standing for. But now the question that I have is, you showed by changing very small changes of these values of U, these Fermi surfaces change rather drastically. So the choice that you did, if it's small, whatever, this is after all what you want. The choice that you did is because with these Fermi surfaces you can explain at least many experimental results. So, because if you choose a different small, you change it a little bit, your Fermi surfaces you were showing look different. So it seems very sensitive to these small changes of the value of U and J. So what makes you decide this should be the Fermi surface, or this really one
So-
issues?
So I think when I use DFT plus U, if things, if results vary much with U, vary with U as it's changed around most probable value, then I take the results with a grain of salt and try to understand why it's happening. In many cases, when you open up a gap, make it an insulator, or you open up a gap in the rare earth F spectrum, then the results don't vary much with U if you use something right. So when it does, and well, you're starting with a very tiny gap here, and they call it the insulator metal transition versus Coulomb interaction. But yeah, increasing U just twists the bands around a little bit, closes the gap, and then creates pretty quickly large Fermi surfaces.
Yes, it does
Unusual.
An effect which is contrary to what we are used to for the D systems, where the U in fact opens the gap.
Right.
So here you go into the opposite direction.
Right.
And even with spin-orbit coupling, we saw that spin-orbit coupling is there, helps, but you go to the metal easily with this U. I mean, it's very interesting to see just the opposite.
Yeah.
They did it for unpolarized case.
All the other calculations for unpolarized.
What about this second superconducting phase, this blue pocket? Standard or whatever.
Especially these papers dealing with this, I haven't read very carefully because
But what's experimentally known about this second blue phase? Upper right corner.
I don't know.
What is red phase?
Red is polarized.
Polarized. And you have another phase diagram. In fact, I was not talking about this one. You have a previous phase diagram.
There was a previous one.
At the very beginning, you have another phase diagram.
Oh, it was.
That was for
Yeah,
the-
this is just the
that's because
schematic.
of the difference.
So, yeah,
That's what I was looking for.
this is suggesting relationship to these ferromagnetic superconductors. Uranium, cobalt, germanium, uranium, germanium-2 over here, and then there's triplet superconductivity, ferromagnetism. This is vastly
This
oversimplified.
ferromagnetic instability is very near. So because you are finding, in fact, this ferromagnetism, it's very. This is the one I wanted to. Yes, this is the
Yeah.
one I.
So this is very, very schematic.
Thank you.
But this high field phase, that must be non-unitary, right?
You're much more the expert on that than me.
Yeah, I don't think there's any other phase that can actually be triggered by non-unitary field.
There were some old theoretical works on people predicted. There were some old theoretical works, I just forgot, Baltensperger and so on. They predicted that at very high field, there may be some cancellation of the in terms of the external field. Actually, we can get some profit. I forgot actually about that. But it was really just,
Yeah, but then when
even
you,
just for the
but then,
standard is
then,
very,
then if you start with ferromagnetic state,
definitely predictions that will
Did you check the calculation of each different orbital? The tetragonal shape and maybe lowest orbital is a special orbital is occupied more. This is
So,
not without this couple.
so this. This gives you an indication. We certainly looked at the occupation matrices that come out, and this gives you the occupations that are, the orbitals that are occupied and half occupied. So you have further question?
Related to this, if this kind of thing is when we consider the ferromagnetic order, without the ferromagnetic order, this is a half filled, but some turn on the ferromagnetic order, this is fully occupied. There is a reason why ferromagnetic order gives the insulator is related to the, if system is half filled, the occupation is two, doubly degenerate band is here, and yeah, 2 electrons is occupied. That case the half field is in the without the ferromatic order, but if you consider the ferromatic order, 2 is fully occupied. That is become an insulator. So that means the induced two orbital is fully occupied, and other is more above the Fermi level. In my, I think this is more.
So I think nobody's yet got into the details of like taking into account the crystal structure and how much second neighbor uranium distances. They're just somewhat greater than the nearest neighbor, and how important this chain, so-called chain of uraniums. So I suppose that's going to be related to how these occupied orbitals affect each other.
Probably we can continue discussions.
For those people who